Hi, welcome back to the channel. When we have capacitors connected in a circuit and current begin to move in that circuit, as charges are being built up across the plates of the capacitors, also potential difference is being set up. This potential difference that is set up is equal to the work done in shifting one coulomb of charge from one plate to another. That is, the potential difference set up V is the same thing as the change in work per unit charge. Now, at each unit charge, there is work done. Now, the potential difference is the measure of work done per unit charge. Now, if V is equals to change in work over change in Q, then we'll be saying that the W should be equals to V dQ. Now, we know that Q itself is the same thing as CV. Now, where my Q is the charge in coulombs, my C is the capacitance of the capacitor, and my V is the same thing as the voltage across the whole capacitor. Now, this charge Q is equals to CV. My C here is a constant. A change in Q, dQ, will necessitate a change in V, so that this becomes C dV. That means if I call this equation 1, let's refer to this as my equation 1, can easily substitute for the Q in equation 1 so that I can rewrite my dW to be the same thing as V C dV. In place of the Q, I've just substituted C dV. Now let's rewrite it properly so that the W is the same thing as CV dV. Now I can integrate both sides so that if I'm integrating this side, I'll be integrating this side. Now if I integrate this side, it becomes W now to be the same thing as C. I can integrate this as V, ranging between V itself and 0, because the potential across the capacitor will begin to build. We imagine it's building from 0 to a final voltage V with respect to dV. So that W, from basic integration, my W now will be the same thing as C V squared over 2. I can easily write W to be half C V squared. And that is how we come out with the formula for energy, or we call it work done, across bits of capacitor. Now, let's take a work example. Now, our question says, since a capacitor can store charge just like a lead acid battery, it can be used at least theoretically as an electrostatic battery. Now we have to calculate the capacitance and energy stored taking 12-volt electrostatic battery with the same capacity as a 40 amp hour 12-volt lead acid battery. Now, from above, we've been given that we have a lead acid battery of 12 volts, now which can be theoretically used as my capacitor. Now, so that my V here is the voltage across the lead acid, which is 12 volts. And it has a capacity of 40 amp hour. That is, my Q here will come from IT, which will come from 40 times 60 times 60, because we're talking in terms of 1 hour, converting to seconds. That will be 144,000. Now, remember that my Q at the same time is the same thing as CV, so that my C here will be equals to Q over V. This will be the same thing as 144,000 over V. My V is 12. 144,000 divided by 12. That's the same thing as 12,000 farad. Now, so that if that's 12,000 farad, I can now begin to think of the energy stored. Remember that our energy stored is the same thing as half CV squared. Now, that will be the same thing as half times 12,000 times 12 times 12. If you compute this, you should come up with 864,000 joules. Because we're talking in terms of energy, we're talking in terms of joules. Now I can just write this as 864 kilojoules. 164 kilojoules. With this, I hope you understand how to work with energy stored across a capacitor. We'll take further examples in our next lesson. Thank you and see you in our next class.